Okay. Well, for people who are joining this live stream, this is a internal design discussion about a potential future Wolfram language feature for solving n-body problems. This is slightly further out than some of the design reviews we've been doing recently. So let's launch. All right. Now, what do we start on here? So let's understand. All right. So this means, what is one arrow? This is, what does the one mean here? That's a mass.
That's the mass.
Okay. As opposed to what we're not doing here is in any way to tag, like Earth, Neptune, whatever. We don't have really a way to do that. Would we ever be able to store that? Not clear.
I think actually so one of the issues I think is that we may want to tag more than one property with a given body. So we might want to have body tag names or something, because for example, in the elastic examples, you need not only mass but material properties if you're going to try and do it using the physics.
Mm-hmm. Okay, so what is this now? And where did these variables come from?
Oh, that
seems to not be doing the same thing anymore.
Right, that was probably a print statement that shouldn't have been there or something like that.
Okay. All right, fine. Okay, so let's take a look here. What is this? So that is from from n-body evolution data, one is able to get, so if I say data one of equations, are you telling me, then, oh, that's kind of cool. So what about the variables? Can I ask for the variables? No.
I didn't. That could be easily set up, but
seems useful to me.
Yes.
I mean, okay. Maybe we should have variables, and that should be an association which has positions and momenta. Could whoever's making that background noise please not do that? And the fact that these are p sub 1 and so on, that seems arbitrary, because it would be nice to have p sub Jupiter, p sub Earth, and so on, right? Am I making sense?
Yes, we could use whatever we want so if each body had a tag of some sort, we could use that as a subscript.
Listen, what I think we should be doing here is these body specifications should be in the following form. So we should have, body tag 1 arrow, and then each body should be able to be given something which says mass, initial position, blah, blah, blah. And that way we can give arbitrary amounts of detail about each body. And the alternative to this would be that we could just give them in a list. By the way, does anybody remember where I was storing? Hold on, I want to save this someplace. Remember if this was in n-body? Yes, n-body problem. Okay. Does this seem reasonable? I think there's a better way to do this. So in general, it would be a list of associations. And as the cheap version of this, hey, whoever's making that background noise, please, can you stop? Do you understand what I'm saying, Rob?
Yes, and I think that's a better way to do it. Now we'd have to obviously require initial position and initial velocities, but anything else could probably be optional.
And then we need a way to get out the list of the things that are required for a certain potential model.
I see what you're saying. So
yes.
So then, and what does that mean, Rob? I think, by the way, you're making this background noise. If you could try to figure out how to not do that, it'd make for a.
I'll try.
The, Okay. So let's just look through here. So let's be noting down separately the design here. Okay, let's actually put this in a. Okay, so the basic thing, do we even believe in the name n-body evolution? Is the word evolution the right word?
I
I
think
think it's more n-body solution, wouldn't it be?
no. This doesn't emphasize the time dependence part.
Okay. So then what we're saying is, but here that's the time that we want it to evolve over, right? So the basic form of this is force law followed by system setup followed by time. Is that correct?
Yes, and the force law can be an association that actually has a potential or a force or different things, and I think I included examples there.
Okay, so look, the system setup. So by the way, I assume units will be able to be handled, right?
Yes.
Okay, because we should do the Earth, Moon, Sun system, for example. We should be able to do that with the actual masses of the particles, right? And we should
Can
be
I
able.
move it? Sorry.
Go ahead.
Can I move it forward by giving as an argument to an n-body evolution data?
That would be nice, wouldn't it? So let's think about this. So this thing returns n-body evolution data, which, by the way, is rather ugly in its appearance right now and should be an actual summary blob.
Yes, I know. This is just a prototype, Stephen.
Yeah, I know. Okay, so then, so what you're suggesting is, I mean, clearly, that's where it should be, is in the system setup. So one possibility would be n-body evolution of force law, and then n-body evolution data. Does that make sense? That seems like a reasonable thing to do, and then that would graph together. Then that would make a combined. But
the force law could be already embedded in the n-body evolution data.
I agree.
In which case, it could just be automatic.
Or you just leave out that argument.
Yes.
I mean, I could imagine I could imagine the case that people might want of being able to change the force law. It's perhaps obscure, but this could be supported as well.
Mm-hmm.
But if you change the force law, where do you give the new parameters?
For what? For the force law?
For
or
the
for
new force law?
Well, in this first argument.
But the first argument is just a string saying what type.
No, I thought it could be an association giving more detail about the force law. Okay, so.
Yes, and n-body evolution of just force law and system setup without a time can just construct an n-body evolution data with just the initial conditions.
Ready to go, so to speak.
Mm-hmm.
Yes, that's a reasonable thing to do. Right. So I'm sorry, with a force law and a system setup, it's not clear that yeah, okay, so. Okay, all right. So it's more consistent, by the way, to say mass, position, velocity than to say initial, whatever I would think. By the way, we're talking about velocities. Why are we talking about p dot? Well, I don't understand what these are. These are the momenta.
Yes. So what I did in the actual solver to try and use the symplectic solver is I solved in terms of position and momentum.
Okay. But you could have written that in terms of the momentum could always be written as a mass times a q dot.
Yes.
So maybe we should say I mean, okay, so we've got extractors here, or properties. And among those properties, let's see here, properties. So one of those properties would be, I think we should say something like position equations or something. Well, no, I don't know, equations. But we want something. Why on earth does that have smart quotes like that? How weird. But then we want, what are these? These are canonical, Michael, what are these called? Canonical coordinates, what are those called?
Symplectic.
Well, okay, but I don't know whether, I mean, we could say something like that, possibly. Where equations is in terms of, I mean, or that could be
P and
something
Q.
like position equations.
But position equations, I would expect that the Q's are eliminated.
Yeah, what happened to these smart quotes in this version? There's something is wrong with these smart quotes. Ah, sigh. Sending that in. Okay, so what are you saying here?
I would expect if you want position equations that the PI have been eliminated.
Exactly, that's what I'm proposing.
Yeah.
But so do you think it should be called position equations and then, but what should just equations on its own do?
Hamiltonian, so basic symplectic.
So that's equivalent to, you
The
think?
Hamiltonian equation might be better, less obscure than symplectic equations.
And that's equivalent to equations.
Yeah.
Okay, so where does it ever say that Q dot is equivalent to the thing that you call position here? In other words, how do I know?
And then we have a variable, a string argument, position variables.
All right.
Yeah.
And what? Velocity variables or momentum variables? These are momentum variables.
Yep.
Mm-hmm.
Okay. All right, let's keep going here. So what's this? Positions? What is that totally weird thing there?
Yeah, so this is a part that's not ideal. We need so the idea is we have this data structure which is useful to get things like equations and stuff, but we want to get properties, the actual evolution properties at certain times. So what's the right design for doing that? This is what I set up. I realize it's not ideal.
Okay, so this is in n-body evolution data, embed. So what background noise? Go. Someone from our live stream is asking, what about rotation of objects?
I think we speak only about point masses, not all of Poisson.
Yet. However, it is worth remembering that we might one day need that. Possibly also think about extended objects. I mean, that becomes more like a traditional physics engine. Okay, in any case, let's point particles. Okay, so what we've got here is, if you just give a time, what should you get? You should probably get a version of this thing.
I think two lists. You get a list of position values and momentum values.
I don't agree. I think you should get something which really looks like the system set up for that time. Because then you can go in and extract, where was Jupiter? What was its velocity? and so on. That seems like the consistent thing to do. If it's just given a time, then it returns a complete system setup for that time. So it's like the forward evolution, like you're extracting. And similarly, presumably, if you give it, so what do we do in, is there a way in ND-solve when you get an interpolation function back, do we have some mechanism where you can ask for like an interval there? In other words, did you get what I'm saying, Rob? Rob?
No, we don't really have a way of so you're saying, reduce the interpolating function to that interval?
That's what I'm saying, yes.
Yeah, I mean that's this old function called function interpolation sort of does that.
Yeah, but what about just feeding in? What about if you just were to give the interpolating function an interval, why doesn't it just return another interpolating function?
Something we never thought of designing. I mean, what's that's going to be expensive, and what's gained?
What do you mean? Why is it expensive?
Well, because you have to reconstruct a whole new interpolating function by partitioning and extracting parts of the data.
Okay, so probably not necessary.
Yeah, nobody's really asked for that.
Yeah, okay, fair enough. Because what you're doing then is you can make a plot. Okay, so now the issue is what happens if you want body such and such at that time, for example, if you only want that body at that time. So then the obvious thing to do, I mean, the way you would get that would be, body spec, right? If I'm not mistaken. If the thing were to return an association always, then that form would give you the mass, position, velocity for that body. And in principle, this would give you the position there.
Yes, that's correct. But in terms of actually, the way our evaluator works, that's not going to be a fast or efficient way to get out the position. So if you're doing a plot, it's going to be quite a few times slower. Well, because n-bed of time evaluates first, and so something has to be
generates
constructed.
all of them. Yeah, I understand. Right. So maybe the right thing to do here would be to support the elided form of this. And then that can default. Oh, I see. Body spec would have to default to all of them because you really don't know. But this would be, so let's see how crazy this would look. So n-bed, yeah, I mean, this is fairly non-crazy. I mean, Jupiter, no, I'm sorry. Time, T, comma, Jupiter. The only thing that's a little unfortunate about this is I prefer to have Jupiter position first and then time afterwards. Am I making sense? Now, one way to do that would be to return here. Yeah, okay, so this is a possibility. Okay, so well, I'm not suggesting this as such, but this would be, so if you did this, and then this returned a spec that said tag 1 goes to, and then the mass is a constant, so that's okay. We can, assuming the mass is a constant, which for these computations that we're doing here, the mass is a constant, right? Then the position could be an interpolating function, etc. So that would be the complete solution. Am I making sense?
Yes.
But to slice that for a specific time. So one way to get, I see. So look, this is a way you could do this fairly reasonably. Okay, if you said solution, comma Jupiter position, then what that would return is a pure interpolating function that just has exactly what you want to plot. So being able to say something like, so then in the actual plotting code, what it would look like is just this. So the only thing that's a little unfortunate about that is the having to have the word solution in there. Michael, are you still with us?
Muted, but yes. I agree. It's a little bit, it nearly would look nicer if there would be arrows in between. Solution goes to Jupiter, goes to position, rather than the pure comma form.
Well, maybe, but I mean, I think even better would be not have to mention solution, just say Jupiter position. But more commonly, this will probably have a, I mean, the other thing one would want to do is to have a solution for all bodies.
Right. I think, yeah, you want a couple bodies, but then want one interpolating function where you stick in the time in the ideal case.
You mean where the result is of the interpolating function is a list of the positions of the bodies?
Correct.
Okay, let's think about that for a second. I think we should move on for a minute. Actually, we have a question from the live stream. Can it give particle positions within a particular geometric region at a particular time without having to do all the filtering yourself afterwards? That's certainly interesting, being able to give a region. How would we do that? I mean, that is being able to answer the question, what bodies are within a particular region?
Well, that would be sort of a post-processing thing for the evolution data.
Presumably. Yes, but I mean, the question is, okay, fine, but then how would one even do that? How would one do that? How would one keep only bodies within a particular region?
So
Using the
I'm not
computational
sure the
geometry.
design, but the way I would do it, with the data I have now, is you would just do, you would pass through the bodies, and you do basically a region, region member queue. Probably,
Yeah.
if somebody requested that, you would set up a fast search for it.
How do you do that? Does region member queue have some kind of region search function?
Well, no, there's sort of, it creates a region member function.
Okay. So
and so
you mean
it would be based
visibly
on that.
so, or by the way,
Yes, visibly so, I
called
think.
region member queue. What is it called?
Region, it must be region member, or
what would one be wanting in terms of a region in this case? You're talking about like a spherical or a rectangular or what?
Yeah, I mean, you want to only look at, you don't care about the asteroid that escaped from the solar system.
Okay, what I'm getting at is, would it make sense just to be thinking in terms of a straightforward nearest function where we're using either the 1 or 2 norm?
No, I mean, actually, on the live stream, someone is suggesting a region function option for n-body evolution, which I think is not foolish.
I mean, if we allow just
what would this do? I don't understand.
Well, there's a question of what it would do, whether it would actually start ignoring bodies that went outside that region.
That wouldn't make any physical sense
no,
for most.
That doesn't make sense. I think you just want to, you could save data only for bodies that are in the region. So it would be a possible way of reducing the amount of data that would have to be saved.
I see. That's interesting. So I mean, that is interesting, because you could do a big simulation and then you could say, I only care about the near Earth asteroids, so to speak.
Yep.
Okay. So what was the answer for whether region member generates a function here? Oh yeah, returns a region member function that can be applied repeatedly. Yes. So it does. So okay, so that's an interesting idea, to have a region function that that determines which things get saved. Okay, let's return though. Let's take a look more at your notebook here. Okay, kinetic energy. Oh wow. I guess that's right. I mean, I guess this is physics, so I guess we can actually ask for things like that. And total energy, wait a minute, kinetic energy is total kinetic energy or total kinetic energy in the system or total, what is that?
Well, again, I'm not a physicist and it's showing, but
I think kinetic energy is fine, but I think potential should be renamed to interaction, and potential should be the one body thing that acts on everybody.
Wait a second. So kinetic energy would be the total kinetic energy, is that right? Of every particle in the system.
Yeah.
Okay. Okay. And then what is that interaction energy?
Between body 1, 2, 1, 3, 2, 4, and so on. Right now, that's everything there. But you might imagine so that the thing doesn't go astray, enclosing the whole thing in an oscillator potential to keep them at bay.
So I'm sorry. Okay? Hold on. Total energy is something that better be conserved. You know, that's the total energy of the system.
Correct.
You know, computed total energy. Which, by the way, you know, you might want very much initially, you might want to say n-body evolution of force law system setup, even before you start computing with times. Even in this case here, you might want to say of total energy, and that would compute the total energy of that configuration. Am I making sense?
Yes.
Yes.
Okay. Okay. So now I don't understand the interaction energy. This kinetic energy thing is a single number for every particle. That seems kind of crazy. Why isn't it just the kinetic energy for each particle?
It's the sum. It's the sum
It's the
over all
total
the particles.
kinetic energy of the system.
Okay, then it should be called total kinetic energy. And the interaction energy is the sum of all the potential energy. I mean, all the pairwise. Because these are pairwise potentials.
All the potentials are pairwise. We only have pair potentials.
Right. Which, by the way, is a note for the only deals with pair potentials.
You also we don't want to paint ourselves into a corner should we go to a multipole or whatever it's called approach to this, where you don't necessarily have all the pairs.
What do you mean?
Well, with the
with this multipole expansion thing, approximating it.
Yes, exactly. So you can approximate the total very well, but you don't even want to deal with all the pairs. That's the whole point, is to avoid that.
Right. Well, so what are we doing here? Do we want a pair interaction energy or do we not?
Yes.
But we can always compute a pair interaction energy. Could somebody who has background conversation put themselves on mute? You can always compute that, right? Given what we say, where we say the particles are, you can always, if you want it, compute a pair interaction energy.
But the same argument is true for the kinetic energy.
That we might not have computed it.
That you, like, once you have the momenta, you can easily calculate the total energy.
Yeah. I mean, maybe that's just a courtesy.
Yes, that is exactly. Both of them are just courtesies.
But the pair interaction energies, how would we return that? I mean, this is just returned as a number, but the pair interaction things require what? An array?
It's just a number. It's just the total pair interaction energy of the system.
Okay.
Yeah, and I think that we definitely want as a total, because otherwise we're talking about, an n-squared matrix.
Yes.
Yeah, which is completely crazy.
Yes.
Right. Which you can just compute yourself if you want to. Okay, this is where it starts getting more exciting.
But sorry. So now if you forgot the potential.
What do you want there?
Like, assume you have something, say you have a gravitational three-body problem.
Yep.
So there's a chance that one flies to infinity.
Yep.
I want to avoid this. So I put the whole thing in an additional oscillator potential. It doesn't fly away.
Okay, so you're changing the potential law.
No. I add a one-body potential from the outside, an external one to everybody.
Okay, but so that's a completely different thing that affects the force law.
No.
That-
The force law is still 1 over R.
But
I put something that constrains the whole thing.
what we're talking about here is properties you can get out, not things you can put in.
Yes. But we had
So-
discussed the last time that we wanted such a one-body thing.
Fine, but then how do you? So that's okay. So you're talking about an option or a change in that force law thing there.
No, the force law is still the same, Stephen.
But okay, how do you specify this? It's something which this is nothing to do with an output property.
So the way it was put, so that's input property. In the way, like I said, that force law could be, as I set it up in the code, and this was on Michael's suggestion, is you could set up an association, and you, for example, so the default is to assume a pairwise potential.
Yep.
Okay, but you can put it as an association, such as pairwise potential goes to that, and then I called it particle potential goes to whatever.
Okay, that seems highly sensible. Okay, so the force law. So you're saying it could be either something like, inverse square, or probably harmonic potential. I would assume you have that. Do you?
No, but I have inverse square. Oh yes, I have harmonic.
It's
Okay.
the same by Christianiano-Stiefel.
What?
They are identical. There's no difference. With Christianiano-Stiefel transform, every can be transformed into each other. That's why these are the two exactly solvable cases, because with closed orbits, because they are the same.
Huh.
By duality relations.
What is that duality transformation?
Christianiano-Stiefel?
Is that, how modern is that? Is that like from a century ago, or is that a modern thing?
50s?
Huh. Is that because, so what's the Runge lens vector being the additional conservation law for
That's not unrelated to the topic at hand.
Okay. But so what is the analog? So wait a minute. This is like I don't understand. I thought, so the gravitational three-body problem is hard. I didn't think the harmonic three-body problem was hard. I thought that
No.
to get like the
Yes.
Fermi-Pastor-Ulam.
No. I sorry. I was now again at one particle.
Oh. Okay. Which is or the two-body case. All right, fine. Okay. Okay, but so the force law is either something like this, either a named force law, such as inverse square or harmonic, or you're saying it can be something which has the form, an association, which is something like pairwise, arrow, whatever. Is that correct?
Yeah, I called it pairwise potential, but because there were some cases where it is actually that Michael had given me where it was actually easier to actually just give what the force
I
between
was just
two
going to say,
particles
we
would
cannot
be.
always assume conservative forces.
Okay, fine. Okay, so then we're talking pairwise. So what you're saying here is that we want something where we can give pairwise potential, pairwise force.
Yes.
And if we given a potential, we'll differentiate. We'll take the gradient of it.
Yes.
That's pretty nice. Okay, so then what is the you want the one particle potential. What are you calling that?
I just called it particle potential.
Yeah, that sounds convincing until the particles are planets.
Yes. Okay.
Fair
There you don't have it.
Well, who knows?
Okay, that would be the viewpoint, like everybody is in the force field of the sun as an outside one.
You
For
could call
example,
it
yes.
you could call it body potential instead.
Okay, that's reasonable.
I would actually call it external.
That's much more reasonable. Yes, because then it could be like a magnetic field or something.
Mm-hmm.
Okay. Do we have any other things here? So we have pairwise force. Is that correct? Or is it?
Yeah.
Yep.
And these things can either be named or they're pure functions. Is that correct? Are they, so a pairwise potential depends only on the difference of positions. Is that correct? Or does it depend on the absolute positions?
It depends on the difference of positions.
Okay, so in this case,
well, actually,
No, that's not true for
it
health.
has to depend on the norm, the vector between the absolute vector between the two positions.
okay,
Because
so pairwise position potential here depends only on vector difference between positions. It's not obvious that that's the right thing in general. In general, you might want something where the pairwise potential depends on the absolute positions of the particles, right? I mean, this is factoring it in some way, but there's nothing about our setup that really requires, you know, I mean, we could have a thing possibly, I don't think this is necessarily right, but something like absolute pairwise potential or something, or position-dependent pairwise potential, positional pairwise potential.
It depends a little bit, like what are the pure function arguments that we want to fit in.
I know, and we could possibly have, but I don't think we want to provide. I mean, it's like a handler function where we don't want to provide more arguments than are necessary.
right.
On the other side, pairwise potential, I feel like asks for give me two.
Well, so you're saying that this one would be something where it's f of position 1, position 2. But what about velocity dependence?
That was my next question.
Okay. I mean, we could have something. I mean, we could start with something like. This is getting very.
I think kind of like if you give more arguments, we take as the next one the velocities.
Well, fair enough, but then what about the masses? Look, in the end, we're going to have the complete system setup. We're going to have the whatever the complete tag is here. Right, we're going to take that association. And actually, that is not completely stupid. Right? If what we did was we gave two associations to the thing, right? Then what it would look like is it would say, well, what would it say? What we would like to be able to say is hash. Unfortunately, if we could say this, I mean, unfortunately, it's going to wind up being something like that to give the position of the first body, and that's kind of ugly, right? Or it's hash 1 position minus hash 2 position, which is not terrible. All right, let's keep looking through some more of this for a minute here. So by the way, I mean, in terms of these plots, it would be really good if these plots were able to be not, you know, if basically the colors were different because these things corresponded to, now how does that work in parametric plot? So parametric plot, if it's fed multiple functions, then
there's some tricky invocation that when it doesn't evaluate to a list, you can tell it to use different colors, and I can never remember what that tricky. I think that should be like one of the first examples in parametric plot, but it's not.
Well,
it's
okay,
like
but
buried
so we
way
need
down in the options.
Right, fine, but we need to then we need to look at how to make that better. Maybe there's a different heuristic for parametric plot. I don't know. Okay, I just want to look through what else you have here, and then I want to loop back to the design. Okay, this doesn't help me very much. I mean, maybe in the phase space.
Right.
So, and by the way, this is an n-dimensional setup. What's happening here is merely that you are giving it whatever the initial positions were. Let's see, that's so far. Dimensionality is determined by the initial positions.
Yes.
Okay. Why have you got an earth in there?
But it was just a way of smoothing it out so that I could actually do something. So it's a smoothing approximation to what Michael suggested as a unit step.
Why do you need that smoothing?
It gives NDSolve a chance.
Don't you have all kinds of event mechanisms to deal with this?
Yes, we could try to do this. That again is a bigger project to try and do things like that. But yes, it's possible.
Well, but let's think about how that will be specified, because this is saying, you know, can you do symbolic analysis of the force law to determine whether you have to set things up with events?
That should be pretty straightforward. You differentiate and see if you get some data functions.
Right. There's some automatic processing. Part of the reason I didn't try to let that work here is because I was trying to use this symplectic method, which is not really something that as it's set up now is going to work with our current setup with it. It's not going to work with the event stuff very nicely.
Uh-huh.
Because it requires constant to keep it symplectic. Okay, to keep the energy conservation, you need to have constant step sizes.
Right. I see. Well, that's okay. So then there's method options. Yes. So I mean, you get one or the other. Okay. So look, the hard sphere gas thing is probably a future set of issues. All right, let's loop back here. Let's just look at that parametric plot question, and then let's loop back to this design. I think we're getting pretty close on the design. I'm pretty happy with this.
I mean, I feel like for the default case, parametric plot could just be smart and take the n-body evolution data.
Yes, why not? I mean, so okay, so plotting. So you're suggesting parametric plot would take what? The actual
the object n-body evolution data open close.
How could it be open closed? It would have to be.
No. Basically, a convenient way would be plot me the whole thing, put me all particles over all times given, not open close. I mean,
then we should make that work for interpolating function as well.
Right.
Which is an interesting idea, which we have not considered because I don't think we've reviewed this in a long time. Rob, what do you think about that?
Yeah, I sort of have this recollection of Brett doing something with like plot of interpolating function.
I don't know.
And it just worked. Maybe it was list plot. There was something he did. He'd be the one that knows what actually happens. But yes, plot of interpolating function or parametric plot would have to be an interpolating function that depends on a single parameter and produces a list.
Exactly, or a triple. Yeah.
This is a pretty horrendous example here. Sorry, what are you saying? So if there is such a usage, it is not documented here.
No.
Okay. Okay, so I'm sorry, what were you saying, Michael?
More or less rephrase what Rob just said. Like, depending on what interpolating function returns, you stick it either in plot or parametric plot.
Well, that's interesting, but wild. But so what do you, I don't quite understand. What?
For normal interpolation, in the example that the ref page that you have open shows, you basically give it a value and you get a number back. So plot is the most natural thing to do. But if you give it a number and you give a pair back, you use parametric plot.
Yeah, but how can you do that? If you just say plot, it's not going to just suddenly jump into being a parametric plot, is it?
No. No, I think we all mean the same thing. It's
Okay,
all fine.
fine.
Well, an
Okay,
alternative way of doing this, which doesn't involve messing with parametric plot or whatever for the n-body evolution, is to have a plot property.
Yeah,
I just
as
wrote
Stephen
that. That's what I
wrote.
just wrote on that.
Oh, okay, I didn't know that's what you meant there. So that's
Yes.
Yeah.
okay.
Yes.
Sorry.
I mean, the problem with that is, what about the options to plot?
Bad luck.
Well, I don't know. I mean, I guess you can do. I'm not convinced about this. I don't think this is the right way to do it.
Mhm.
But let's go back down here, because this is something that's needed for the basic implementation, is to decide what you actually feed to the potential functions. Okay. And in particular, when you say inverse square, what is, and by the way, I mean, when we say mass, we don't necessarily mean mass, do we? We mean weight of some kind, which will confuse people if we call it weight, multiplier, or something, because it could be a charge, for example.
But we use, in some sense, F equal MA. So M has a very special status.
Okay, fair enough. But what
Yeah,
if these are
I think if
charged
somebody
particles?
wants to do charge, they should have charge in that association.
Fair enough. So then, in that case, what should happen is that association. Okay, so then we could have things like charge here, could be another thing there. Fine. Okay, so then what should happen is that in the pairwise potential, then the most natural thing for the pairwise potential to do is to take there a SOC1 and a SOC2, I believe. So how would that actually look?
That will be a little bit hard, because like the charge that you just added, so we need non-trivial knowledge how to build the force from the charge.
No, but I'm saying if you give the pairwise potential there is, okay, so this is the first association. All right, so this would be something like #1 charge times #2 charge. Let's write it out.
Okay,
Divided by
4 pi epsilon 0 and so on. So the question is, how do you encode this stuff?
Well, I'm suggesting that what happens is that we'd say pairwise potential.
Oh, I see. You shifted 100% to the user.
Yes, that's what I'm
Okay,
saying in
okay.
this case. So let's write out the whole thing. Okay. So then what that would be is divided by, so we're wanting the potential. We just would then want to say norm of #1 position minus #2 position, right? I mean, that seems about as reasonable as you're going to get.
Assuming charge, the values for charge are dimensionless.
Oh, okay. Yes, Michael, we've got a 4 pi epsilon 0 in there as well.
But I'm saying, like, assume they would be not dimensionless. Then this would fail now, and it should probably fail. We should not automatically insert this 4 pi epsilon 0.
Absolutely not.
Okay, that's what I'm saying.
Absolutely not. But we do need to pre-process these things to get rid of units, right, Rob?
Yeah.
Right. Yeah, this whole thing of handling things like this is a pre-processing step.
Yeah.
Exactly. Yeah, it just gets rid of all this stuff. Now, the default here would be, I mean, I think here, so inverse square means, so pairwise, but so just inverse square means gravitational inverse square. And we could have an electric version of that, which expects charges. Am I making sense?
Yeah.
Mhm.
Should we call it electric inverse square or?
Coulomb.
Oh yeah, that's right. Coulomb law. Okay, so that would expect charge. I think this is pretty reasonable and pretty nice, actually. So then external potential. So this, by the way, by giving position literally here, we are dealing with the possibility that we could have a potential that depends on the absolute position. So it is
Right.
not, in fact, the case that we're looking at that, and we have no reason to look
Yes.
at that. And we have no reason to have that either. And in terms of velocity dependent, it's like, who cares? We just put it in there. We don't have to specify that separately. So the only point of pairwise potential is that we're taking every pair here and we're doing this, right? So it's like an outer of those things.
Yes.
Am I making sense? So in principle, one day we could add a 3-body potential.
Yeah.
I mean, actually, it wouldn't be very difficult. It would be 3-body potential. Actually, why are we calling it pairwise? Why isn't it just pair potential?
Fine.
And this could even be triple potential. And then the other one is, and so that would also be pair force. And the pair force would return a vector, right?
Yes.
Pair potential returns a scalar.
Now we'll have to, choose a sign convention for the vector. Namely,
Why?
is the pairwise force
Yes.
the force of 1 acting on 2 or 2 acting on 1?
I understand. Okay, what's the right convention?
I think 2 acting on 1.
Okay.
It's the force that 1 experiences.
I think that's
okay.
I think
2
I agree
acts
with
on
that.
1, i.e. force experienced by 1.
Yeah.
Okay. Well, that also defines what would happen in the triple case if we care about that. So now what are we calling? So we're calling it external potential, pair potential, triple potential, if we have triple potential. And so these things like inverse square. So we could in principle say pairwise, pair potential, arrow, inverse square, and then we could say external potential, arrow, some random ambient gravitational field or something.
Yeah.
Okay. Actually, I really like this way of extracting information. Now, one question to ask is, how does this correspond to what happens in the system modeler business? We should at least ask those guys. Rob, do you know the answer to that?
No.
Because they have a similar mechanism for extracting properties of things. And they have a similar mechanism for doing a simulation plot type thing. So look, I think this is good progress. Now, how close is your implementation to something real?
It's quite a ways.
Why?
So, okay, so numbers of things. So this just calls ND solve, and it just sort of brute force puts together the equations, which for a few bodies is not terrible, but as you get to more than just a few bodies, it becomes quite problematic. So the right way to do this would be to do, to write a fast multipole, fast multipole expansion code to actually
Yes.
compute the right hand sides.
Yep.
Okay,
Which is
there's
what
another issue.
Yeah.
Which is that, and this is to me the more interesting part of it, but of course it's the more time consuming part, is so this symplectic method is designed to work with fixed step sizes. So Mark and I talked about this a little bit. So if we wanted to use the symplectic method, we could do that, but we'd have to do what we'd have to do is we'd have to sort of do an energy monitor, and when you're getting an interaction that's not sort of being include in the step, the energy sort of goes wacko. So you'd have to sort of go back and reduce the step size as you get to closer and closer interactions. And I'm not sure how complicated that would be. Our other methods in AnySolve will probably get that correctly, but we'll have to be very careful about, you know, stiffness, because if the problems do become stiff near close interactions, then we're evaluating a Jacobian, which is absolutely, you know, which for these things could be absolutely enormous.
Right. Sounds hopeless. Right. Look, in terms of a path forward, it seems like we should do the following. We should try to get to the point where we have an experimental version of this function that could actually be put in that will work decently for small numbers of bodies and that has the right design. Okay. Then separately, we need to fork off a project to do a fast multipole code. Okay. Which can then be basically slotted into this thing. But I think we should debug the design before, you know, I mean, that will be a fine thing to fork off. But I think, you know, if we got all the pre-processing and so on done and all this design stuff done, then we're in much better shape.
Yes, yes,
And I think we're decently close on this design. I mean, we should have another meeting.
Right.
So let's.
Well, something that you did before I never got to mention is the total kinetic energy. How do you get out the total kinetic energy as a function of time?
Good question.
So that.
Well, I would assume that this is every one of these things. Let's think about that for a second. So you had the idea here of having this with time do something. It is not completely obvious that that's a good idea. In other words, it might be better to just not have that case.
I agree. I think it's better not to have that case.
Okay.
And then we might avoid the whole solution thing.
Exactly.
Yes.
Exactly. So in other words, okay, all right, fine. Let's rethink this for a second, okay? So let me just okay, so then this would be this thing here with no arguments would be the whole thing. Now that's kind of stupid too. Yeah, the issue is, how do you get out? Well, so this is, all right, so let's say that you have, you've got a particular body, Jupiter, or one, body number one, position. And that could either have comma time, or it could have of time, which would give you the interpolating function first. And this potentially could be equivalent to maybe so if that was the case, then the obvious thing to do would be to have, you know, then it's completely natural that we could say kinetic energy, and what would come out is an interpolating function.
Yes, and we can type kinetic energy comma t gives the particular time.
Yes. Someone on the live stream is emphasizing again that this should be called M-body simulate, and it's not obvious it shouldn't be, and that there's a I'm kind of warming to that idea, and I think that would correspond better to the actually what we have in a different world is system model simulate. Do we not? What is it called? this the wrong version? I'm now confused. Where is that? Is it not merged? There is a system model simulate. This requires, listen, the next one of these meetings, we need the folks from the system modeler team in here. Oh, that's funny. The person on live stream is pointing out that n-body simulate has an N, just like n-integrate has an N. That's funny. That is funny. And yeah.
Could have a double N.
Right. That's funny, and not
Don't think
necessarily.
we'd ever have an exact version.
What's that?
I don't think we would ever have an exact version.
Well, that's, yeah. People say the three-body problem can't be solved, right? Unless we give whatever Sundman's solution or something.
Yeah.
Which would be funny, and if not very useful. Okay, but there is a system model simulate. Yeah, there we go. System model simulate, which actually is somewhat analogous to this. Actually, this is interesting. I mean, this is still experimental, but this is interesting to take a look at as a sample of how one thinks about this. I mean, I do assume that we don't already have code in there for doing this problem.
It's very improbable, I would say.
So notice that system model simulate returns. Okay, system model simulation data, and then it has a system model plot that does this, where you can tell it, I want to see these particular variables. And it plots over the complete integration range.
Yeah, that's actually a reasonable way to do the plot, the parametric plot.
I know, but we want to do it I mean, we can't have a very special plotting function just for n-body problems. All right, so this we have to look at. And can we make sure next time that we include the system modeler folk in this design meeting? And I think, though, that we are, Rob, you should be in a position to actually update your implementation to correspond to what we're talking about here.
Yes, I think I can do that. It's, there's
still some issues.
There's still some issues, but I can certainly update it to do that. I mean, most of the work is in doing the parsing of the functions.
Right. Which I think we're looking fairly good on. All right, sounds good. Let's wrap this up. Very nice, really very nice. Okay, to be continued. Wait a minute, somebody is just, I'm sorry. Oh, no, somebody's asking a completely different question about server farms for Wolfram Alpha. It's interesting. I don't even know where we are in the. As a matter of fact, my very next meeting, which I'm afraid is not going to be live streamed, has to do with Wolfram Alpha, which so I will ask that question there, and if we get an answer, ask this question again on another live stream, and we'll try and answer it. All right, got to go here. Okay, thanks a lot, guys.
Okay, good.
See you.
Bye-bye.
Bye. Bye.